Hello, everyone, and welcome to The Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain.
Later on in the show, I'll be speaking with Dr. Nathaniel Putzig from the Planetary Science Institute about just what might be under Mars's south polar ice cap. We're looking for water, and recent research says we found subsurface lakes of it. But Dr. Putzig was part of another team that said, hold up, did we really? We'll chat with him about why it's important to examine all the possibilities. But first, let's look at the news.
One of the most important science questions today may be, is there life on Mars? Early images from Mariner 4, 6, and 7, and 9 made it clear that Mars is a modern-day desert and no cities or seas dot its surface. Subsequent experiments by the Viking landers are generally interpreted as indicating there isn't microbial life on Mars, at least in those locations. But the results of those experiments are still actively debated more than 40 years later. Since those early experiments, we've learned several important facts about Mars. It had a watery surface in the past. It has subsurface ice and possibly subsurface salt water. And microbial life on Earth has figured out how to survive in Mars-like environments. There have also been confusing observations of methane made by Mars Curiosity rover. Methane is destroyed by sunlight over time, and any methane that is observed has to be freshly produced. Methane has two major sources, biology and geology. And we had thought Mars was both biologically dead and geologically dead. This methane detection indicates that either life, geologic activity related to magma and volcanism, or both exist. I personally am rooting for the or both. The reason these results are confusing is because there are extremely sensitive atmospheric sensors orbiting Mars that haven't been able to replicate these detections. There is every reason to believe both the orbiter and rover are working perfectly. So how can both be right? Turns out that measuring these gases is an energy-intensive process. So the orbiting ExoMars Trace Gas Orbiter with its solar panels was making its measurements during the day. Mars Curiosity, with its radiothermal generator, was taking its measurements at night when other instruments weren't active and the detector could have all its power to itself. In new models from a team led by Christopher Webster, scientists have shown that in the cool Martian night, the air is still and methane can build up near the surface, where Curiosity is sitting. During the day, the circulation of the atmosphere scatters that methane to undetectable levels. To prove this theory, the team had Curiosity do something new. It looked for methane during the Martian day, and it didn't find it. Over 2 days and 1 night, Curiosity repeatedly sampled methane, or at least sampled for methane. And during daylight, it wasn't there in sufficient amounts to be detected. This not only explains ExoMars' lack of detection, but it also reminds us methane is, somehow, seeping to Mars' surface regularly. Now we just need to sort out how. From clouds of methane on Mars, we now turn to clouds of mixed hot gases in a galaxy cluster. A favorite target for astrophotographers with large scopes, the Leo cluster, or Bell 1367, is about 300 million light-years from Earth. In 2017, astronomers taking images designed to reveal the faintest structures in this system found a small, warm gas cloud. These observations were made with the 8-meter Subaru telescope in Hawaii. Follow-up surveys of this system with the orbiting XMM Newton scope determined the gas is hot, but not as hot as normal intra-cluster gas. It's also not distributed normally. Instead of being distributed throughout the cluster in a smooth distribution that is hottest and densest in the cluster center, this material is just coolly hanging out off-center. Its temperature is actually consistent with what is normally found inside a massive galaxy. And in a new paper in Monthly Notices of the Royal Astronomical Society and led by Chang Ji, researchers explain that this is likely a cloud of gas stripped out of a galaxy that has since journeyed on to other places. This is a cool new snapshot of cluster evolution. We knew clusters stripped galaxies of gas. We knew that gas got incorporated into the cluster gas. And now we know, well, we know this process takes enough time that sometimes, just sometimes, we get to see the gas without the galaxy. Galaxy clusters are part of the large-scale structure of our universe. Over the past 13 billion years or so, what started as an almost smooth distribution of matter has evolved to a Swiss cheese of walls, threads, and clusters of matter defined by the gravitational pull of more massive regions on the now emptying voids of lower density regions. It has long been thought that galaxies should stream along the walls and threads toward the highest density regions. And now, for the first time, a galaxy has been caught doing just that. Radio, optical, and X-ray observations together describe an active galaxy that has two large jets streaming out of its central supermassive black hole and getting bent to stream behind the galaxy as it moves through the sky. According to study lead author Angie Veronica, the jets of matter are streaming out behind it like the braids of a running girl. It's always amazing when the science is right and the images are weird and awesome. After a break, we'll be back to look at science that we may or may not have right, the science of the expansion of the universe. Stay tuned. One of the weird things that can happen as measurements get more precise is unknown errors crop up. Need two pieces of pipe to be the same length? Well, in building my old house, that would call for a pencil, a ruler, a fancy blade used only with goggles and a bit of trepidation. And those pieces might differ by a millimeter here or there. But heck, the house was built in 1893, and anything better than a centimeter, I'll take it. Now, if you're building something for LIGO to measure gravitational waves, digital calipers and lasers are likely to be involved, and differences may be measured in wavelengths of light. This means a bunch of pipes I see is all pretty much the same size. To LIGO engineers may all appear pretty different. And it may turn out that the differences between cutting on the inside of the pencil line and the outside of the pencil line can lead to more sensitive measurements revealing two different sets of lengths of pipe. In trying to measure the expansion rate of our universe, we've used a lot of different rulers, and we've even strung them together awkwardly since no one tool can measure the full distance back to the beginning of the universe. Any issues in those rulers can lead to errors that get multiplied across everything else. As hard as these measurements are to make, our ability to make accurate measurements has been getting better and better, and over the past several years, we've started to notice that one set of measurements, those that look at the cosmic background light, yield one set of values, and measurements that look at nearby and middle distance stars and supernovae appear to have a slightly different value, and those values don't quite match. Now, a review paper by Wendy Friedman, one of the scientific heroes of these kinds of measurements. That paper reveals that it looks like while our cosmic microwave background-based measurements seem to be more like the high-precision digital caliper measurements we'd like, the measurements from the stars and supernovae may have been made with not entirely accurate rulers that added errors. Specifically, we calibrate our supernova distance measurements using red giant stars and Cepheid variable stars. And she finds that improving understanding of red giants is shifting the distance scale just a bit. And the direction of that change brings supernova measurements in line with cosmic microwave background measurements. Now, a similar error hasn't yet been found in Cepheid variable stars, but Friedman points out that those measurements could easily be affected by dust that exists in the vicinity of these young stars. Simply adding a bit of dust and the changes in apparent brightness that dust could cause That's enough to also bring things into alignment. I'm sure this won't be the final word on this science. If the discrepancy is real, it would indicate there's new physics that could lead to a Nobel Prize. And let's face it, folks, scientists are willing to chase Nobel Prizes into dark scientific alleys. For now, though, I will actually sleep a bit better knowing there probably won't be any weird new physics to complicate our universe. After the break, we'll be back to talk Mars with Nathaniel Putzig. Stay tuned.
Earlier this week, we brought you a story about how a new analysis of bright reflections found in ESA's Mars Express MARSIS data revealed the possibility that what was once thought to be liquid water beneath Mars's south polar ice caps may actually be some other substance like clay or salty ice. New possibilities are on the table, and while they do not exclude the existence of liquid water lakes, they do mean that we need to use caution before accepting the result. After all, a crewed mission to Mars will depend on Martian water resources. With me today is Dr. Than Putzig of the Planetary Science Institute. Than is a co author on a new paper published in AGU's Geophysical Research Letters. He is also a senior scientist here at PSI and works on, well, pretty much every Mars mission out there, it seems. Thank you and welcome, Than.
Hi, Beth. Thank you very much.
You've been on this show before. Thank you for coming back on it. That says something really nice about us.
Yeah, sure does. I really appreciate your giving some airtime to the work that we've been doing.
So, how did you become involved in this particular research?
Well, so I'm involved with the shallow radar instrument on the Mars Reconnaissance Orbiter, and have used that data extensively to analyze the polar caps of Mars and other features. One of the things that we're doing a lot is looking for buried ice in the mid-latitudes, for example, as a resource for future human missions. I've also been involved in studies of the South Polar Cap in particular. With our instrument, the shallow radar, we don't see through to the base of the polar cap in this region where the MARSIS instrument on Mars Express has detected these very strong returns.
So, can you explain the original result from the paper, the one prior that says that this is liquid
Sure.
water? How did they come up with that conclusion?
Right. So they actually noticed quite early in the mission that they seem to be getting some strong reflections off the what appeared to be the base of the South Polar ice cap on Mars. But there were some issues in trying to understand exactly what the data was telling them. Part of the problem was the onboard processing of the data, their standard collection methods, summed together an awful lot of data all at once. So it sort of smeared out the results they were getting. So after many years, after this first hint that they were getting these strong returns, they changed the way they were actually acquiring the data to not sum it together quite so much before sending it back to the Earth. And so they had this better, more finely sampled result. And it showed that on repeated observations of these particular locations, they get an extremely consistent, strong reflection from the base of the ice. In their analysis of it, they found that the reflection from the base was actually stronger than the reflection that you get at the surface of the ice. And this is pretty unusual and speaks to there being something special going on at the base of the polar ice cap.
So they determined that, well, they I don't know if they determined, but they said that what they think it is liquid water, subsurface liquid water lakes. So your team is saying, well, maybe not. What does your work, how did your work change the possibilities?
Sure. Okay. So let me explain a little bit more about their analysis. So effectively, what they were doing was comparing the strength of that reflection from the base with that of other materials, say, that have been studied in the laboratory or elsewhere on Mars, and using an estimation of the so-called permittivity. This is um, the extent to which a material is polarized by an electric field. So they can get a measure of that permittivity from the radar data. Um, and looking at materials, different materials that have these values of permittivity, in their estimation, the only reasonable explanation was liquid water. Um, there are certainly other materials that could have these very high permittivity, such as metals, but the presence of metals at the base of the polar cap isn't something really expected to be there. So they held up liquid water as the most likely explanation. However, there's more than one way to kind of skin the cat with the radar data. Um, so in addition to estimating permittivity, one can use the data to get an estimate of so-called conductivity, the electrical conductivity. And so this is the extent to which a material will allow electrical current to pass through it. Just it's a
Right.
slight difference from the polarization method. Um, and
So what you're saying is the two things used different methods.
different methods of analyzing the data's result, yes. So
Okay.
different measures from the same data set.
All right. Well, I want to talk to you about some more of the possibilities and where we're going with this data, but we're going to take a quick break and then we'll be right back.
Great.
Welcome back, everyone. Once again, with me right now is Dr. Nathaniel Putzig from the Planetary Science Institute, and we are talking about water on Mars, as always, it seems.
Mhm.
So, Than, what does this result mean for the prospects of liquid water on Mars? Does this change anything?
I think it opens up more questions that that need to be further considered. One of the difficulties here, of course, is that this detection is below 1.5 kilometers of ice near the south pole of Mars. So it's pretty inaccessible for direct sampling.
So, what are you working on now? What's next?
So I am presently, I mentioned that the one of the things that I do is work with these radar data sets and other data to analyze the mid-latitudes of Mars. So these are more accessible for humans, and in fact, there's big plans afoot to send a new spacecraft to Mars called the Mars Ice Mapper. And so we're very actively using the radar data sets to look for buried deposits of ice in the mid-latitudes, where people would be able to access them in some of the first missions with humans. So this has been very exciting to be involved in this work. In addition, this ice is of interest not just for resource, but as an astrobiological target. That ice may contain existing life or remnants of past life. And so it actually does tie in a bit with the potential detection of water ice below the south polar cap, which is again a very interesting astrobiological. Well, it has implications for astrobiology, since that liquid water could potentially sustain life.
Well, thank you very much for joining us today, Than. This has been a great discussion, and I look forward to having you on the show again. I'm sure we will with whatever new results you have out. So thank you once again for joining us.
Well, thanks for having me. I really appreciate the opportunity to talk with you about this.
This has been the Daily Space.
As a reminder, we are taking next week off. Want more of us? Check out CosmoQuest.org and get tickets for CosmoQuesticon, our 80s space party that will take place July 16 through 18.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the donations of generous people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.